Welcome back. In the previous session, I explained to you the content and the learning outcomes of the first chapter in the course of discrete mathematics. The first chapter is about logic and proofs. Logic and proofs are very important in discrete mathematics, are very important in mathematics in general, but also very important when we talk about computers, programs, and computer systems. There is first of all the logic part in the element, so we'll be looking into logic and we will be looking into proofs. Now, in the first chapter, this first session of the first chapter is just an introduction about the logic and the proofs that we will be talking about in this chapter and in the following sessions. Now, when we look at the origin of the rules of logic, we typically go back to what we call the mathematical logic. And the mathematical logic is in fact a way that mathematicians developed to stop talking nonsense. The definition can be said as the discipline developed by mathematicians to stop talking nonsense. Why is that important? Well, if people start talking about rules, about logic, it's very important that the people understand each other, that they know what the links are, how do these things work. And it has proven very useful to create a logical system that can be understood by many people, by the mathematicians worldwide. And this discipline is in fact helping the mathematicians to share their ideas, their proofs, their theorems with each other in a universal language. Let's have a look at an example of some rules of logic. When we look at the rules of the logic, they help us to understand mathematical statements. And an example of a mathematical statement is that for every positive integer n, the sum of the positive integers not exceeding n is equal to n multiplied with n plus 1 divided by 2. Now, we can write this in a mathematical format using the summation sign, and the summation just says I'm adding the numbers 1 plus 2 plus 3 plus 4 and so on till I reach n. Basically, in our expression here, we start from 0. 0 is the first positive integer. So here we have a sum going from 0 to n, and we can in fact prove in mathematics that this sum is equal to n multiplied with n plus 1 divided by 2. So let's consider a very simple calculation. Let's say we look at 0 to n equal 3. So we have 3 times n plus 1, 3 plus 1 is 4 divided by 2. It means that this sum is equal to 6. And we can prove that or verify that very easily, because if 1 plus 2 plus 3, 1 plus 2 is 3 plus 3 is 6. So basically, this formula is a more general format that we can use for any value of n. Now, what is logic? Logic is in fact the basic of all mathematical and automated reasoning. Mathematical reasoning and automated reasoning are founded on the basis of logic. There are rules how to deal with logic and logical statements. These elements are very important when we are looking at the design of computers. The computers are basically logical machines that follow logical statements, logical combinations to do certain tasks and activities. It's also very important to consider proofs. Logic and proofs go together because a proof is in fact a way to find out that a mathematical statement is correct. we have a mathematical statement like we had before. The sum from the integers from 0 to n is in fact n times n plus 1 divided by 2. In mathematics, we have proven this, and we can call a proof when we have proven a statement, we can call it a theory. And it's very important that when we have a statement, that we know that this statement is valid in all instances. If we have a theorem, a statement that has been proven in its generality, we can use it in many cases. It can be dangerous when we have a proof that it's only partially correct. And in that case, we have to be very careful. We have to be able to prove the mathematical statement to be correct for all possibilities. Now let's have a look at an example you may still remember from high school or from university when you had the course of trigonometry. The basic equation of trigonometry is in fact the statement that the cosinus to the square of an angle alpha plus sinus to the square of the same angle is equal to 1. Now we have to prove this. One of the things is that we can prove this expression, and we start with the proof that this expression is correct. Now we start in fact with an x and y system, and here we have selected half a circle. In fact, we've selected the first quadrant. Now what we can do, we can construct a line segment or a point here, which is characterized by the coordinates x1 and y1. The length of the segment is r, and the angle between the segment and the x-axis is alpha. We have here what we call a rectangular triangle, and we know that the sum of the corners is equal to 180 degrees. So we know that the angle between the line segment and the y-axis is equal to 90 or minus alpha. We can use here the theorem of Pythagorean Theorem, which is in fact x1 to the square plus y1 to the square is r to the square. This is something we've proven before, and we can use this as a basis to prove the equality cosinus square alpha plus sinus square alpha is equal to 1. The first step, what we do is we divide this expression. We divide both sides, left-hand side and right-hand side, by r squared. Do not forget, whatever we do to the left-hand side, we also have to do to the right-hand side. And we find here that we have x1 divided by r to the square plus y1 divided by r to the square is equal to 1. So we already see that we have those two squares which are equal to 1. Now, when you remember well, in the trigonometry, we defined the cosinus alpha and sinus alpha. And in our case, we have the cosinus of alpha is the projection of the point x1, y1 onto the x-axis. And that's in fact the cosinus of alpha. So x1 divided by r is the cosinus of alpha. And we also know that y1 divided by r, the projection on the y-axis, is equal to the sinus of alpha. And when we replace those, so we have x1 divided by r is cosinus alpha and y1 divided by r is sinus alpha, we basically find that the cosinus to the square of alpha plus the sinus of the square of alpha is equal to 1. And that is basically the proof that we were looking for. We can say we have proven that the expression cosinus square alpha plus sinus square alpha is equal to 1. And this means that it becomes a theorem. So we're going to look at more of these things in the following sessions. So we will start with the next session after completing this where we are going to look into the content and the learning outcomes of the first paragraph of chapter 1. This is the first part that we are going to do. We will see what are the different parts in the first paragraph, and after the first paragraph, of course, we will continue with the following paragraphs until chapter 1 is completely finished. So this was everything for this first presentation of chapter 1, really the first presentation of this chapter. We will go on with the following presentations. So this was already a good start. I hope you enjoyed the presentation, and I'm looking forward to seeing you in the next video. Thank you and bye-bye.